the first one, we are starting to see some curved graphs. You saw your first curved graph in the motion sensor lab. You saw another curved graph, or you're going to see another curved graph for the wheel lab. And we want to make sure that we understand how to interpret these. So for the first one, we've got a position. Remember, X represents position versus time. And the description is that it is accelerating forward and that the position increases as time continues. So it is moving to a further position over time. Then, at its peak, it begins to maintain constant speed. Are there any comments, questions, adjustments? I can think of a few. Anyone want to add or subtract? Okay, so what I want to talk about is the word acceleration. In our everyday life, we talk about acceleration in terms of speeding up. In physics, acceleration means a change in velocity. That could mean speed up, which is how we interpret it. It could mean slow down, or it could mean a change in direction. So when I ask you to describe the motion of something, I want you to not just tell me it's accelerating, but tell me how it's accelerating. It is accelerating by speeding up. Or is it speeding up? What was your interpretation of accelerating? Was it speeding up or was it just change in speed? Just change in speed. Okay, so in that case, this is correct. It is accelerating. But what I would say is we want to describe the type of acceleration. So can anyone give me a description of what type of acceleration it is? Is it speeding up, slowing down, or changing direction? Any thoughts? Nobody? Can someone give me a guess? I know what to do. Speeding up? What do you guys think? DJ? All of them? All right, let's do a vote. How many of you say this object is speeding up? It's all right. We got about 3, 4. How many of you say it's it's slowing down? I've got 2, 4, 5, 6, 8, 10. So a few more. How many of you think that it is just changing direction? And you can vote on more than one. So I've got probably 3. Okay. Here's the way to analyze this. We know that this is the position. I'm going to write it down so that you don't get X confused. And this is my time interval. Let's say it's 1 second each time. In order to determine how far it travels, we need to look at each interval of time. And I know I didn't include this in the graph, but if you just picture this in your mind or even draw it in your paper, the first second, that's got a pretty big distance, right? And the second, so I'm going to call it change in position. Here, we've got a change in position that gets slightly smaller. This is even smaller. And then this last one, does it look like it's changing position? Barely, right? So what do you think now? How many of you say that it is speeding up? How many of you say slowing down? Good. I better see everyone's hands up. If you look at it section by section, you can see that these positions get smaller and smaller and smaller. Does that make sense? All right. So let's add this to here. It's accelerating forward, but it's accelerating in the sense that it is slowing down. Add that to your papers. That's important to know for curved graphs. The position is increasing as time continues. Then at its peak, it begins to maintain constant speed. Can anyone tell me what they think that constant speed is? 0. Constant speed of 0, because this, we don't really know what happens, but if we just look at it, it looks like it's just flattening out, right? So when it's a constant speed of 0, what is happening to that object? How is it moving? Or is it moving? What do you guys think? Constant speed of 0 means what? It's standing still. Thank you. Roberto snuck in and saved the day. Constant speed of 0, object at rest. Ends, let's say ends its motion at rest. Okay? The second thing I want to talk about is the other graph. Are there any questions on the first one before we start? Okay, this other graph, it says the line position starts at a fast speed, accelerates backward. So I'm going to underline this until it reaches 0. So let's think about what it says here. Starts at a fast speed. Now that we've analyzed the first scenario, what do we think about the change in motion? What do we think about the change in speed for this one? Does it start at a fast speed? Let's look at the change in position now. Let's say this is 1 second, 2 seconds, 3 seconds, 4 seconds. Change in position starts here and ends here, delta x. Change in position starts here, delta x. Now, what do we notice about its distance? What do you guys see here? Over time. Is it starting fast? Does this look like a fast change in position to you in 1 second? Not so much, right? So we're starting off slow speed, and moves backward until it reaches 0. Any questions on why it doesn't start fast, but it starts slow? One thing we can say, it increasing speed backward. Okay. Questions, comments? Kaylin.
For the second one, is it like the terms supposed to say decelerating?
You can say decelerating. And the definition of decelerating does mean slow down. And I would take that on a test or a quiz. Yeah. If you use accelerating, though, you have to specify, because decelerating is a type of acceleration in physics, in the physics term of acceleration. So any questions on problem number 2? Okay. In your lab, do you guys remember having to do these midpoint time calculations and velocity calculations? Average velocity? Nod your head, because I do know that you guys remember. It was last week, but we did this. Everybody did this. You guys were really productive, and I was really proud. Basically, what you did was you took 2 points on your graph, and they were data points, but you're going to graph them today, and you basically connected them to get the average velocity. This is your average velocity. You also put on your data table the midpoint time. So this is 0.5 seconds for the midpoint time. And I can't spell. Okay. The reason why is because analyzing the slope between 2 points of your data also gives you the change in speed. Notice how steep this velocity slope is. And now notice how shallow these 2 points are. That means that at the beginning it's moving fast. Toward the end, we've got a shallow slope, so small slope. And this is moving slow. Again, it is slowing down. We can show that not only by the position difference, but also by the slope of each segment. So, you all did a calculation, you shared it with your team. We're going to continue this calculation in class today. Before we do that, I'm going to present a couple of videos because it is National Coming Out Day, and I want to make sure to support all our LGBTQ faculty, students, staff, teachers. And so I added to our little warm-up a presentation by, one is just a general one to celebrate National Coming Out Day, but two is to highlight one of the important scientists in the LGBTQ community. So let me play this really quickly. Hold on. Let me get my lights down. Let me get my volume up. Okay. I have one more. And one more. Okay, take a seat. I have one more video to show about Dr. Lauren Esposito, and I'm going to share. She does have a website as well, which is linked here. All right, so you do have a link to this in your warm up, which you guys all know. At least you should know that this is all on campus. But I do have the link that Dr. Esposito put together for 500. There's 500 of them. I scrolled through this whole thing, and it took me a long time to get through. But there's 500 scientists on this list, and I was hoping to get some posters of scientists. That didn't happen, so I do have a few posters up here, and they're small, but I put them next to the cell phone dock so you could see them as you put your cell phones in and as you pick them up. But just take a moment. We are having an event in the hallway to just write down some of your kind of positive messages to our LGBTQ community here at LGHS. I am a huge advocate for that group. And I have this quote, which is my favorite quote, that says, "Be yourself. Everyone else is already taken." I feel like in high school, Sammy, I feel like in high school it's really hard to do that. And honestly, it doesn't really happen until you're like in your 30s, unfortunately. But everyone is trying to be like someone else. And really, it's important for you to just own who you are, be proud of yourself, find your people that have the same interests, and be able to be in a crowd where you feel comfortable being yourself. So I think that's super important, especially on a day like today. So please provide support. Go into the hallway. They're having events during lunchtime. And then I think, I wish I saw more rainbow, but if you're wearing rainbow on you, you do get candy to just thank you for your support. So I appreciate you guys being giving your attention to this quick little spiel. Let's get into some graphing today. So let me pull this up really quickly. My tech managers, period 4, tech managers. You're gonna do some tech today, and you're gonna print your graph out to what room?
107.
107. And I want to make sure that you print it out on landscape view so that your group can have this graph. And I want to make sure that I can see both graphs. But for all my yellow peeps, pay attention closely. You are going to pop into your Canvas on the computer. Make sure you log out once you're done. For today's date, there is a graphing template. You are going to make a copy, and you are going to start entering, if it'll let me make a copy, you're going to start entering all the position time data that your group collected. You did a few calculations for velocity and midpoint time, but I'm going to tell you right now, this Google Sheet is going to populate that for you. So what I want you to do is check your answers. Did you calculate segment 1 correctly? Did you calculate segment 3 or segment 5 correctly? Okay, Sammy? Do you know what's happening?
Yeah, entering in our data points onto big old document.
And checking your midpoint and velocity answers, okay?
Gotcha.
Once you do that, you are going to print. On Apple computers, it's Command P instead of Control P, and you want to make sure that it is landscape mode. All right? Once you print it, then you want to answer the rest of these questions. I'm going to stamp your lab today. So make sure you get it done in class today. All right? This is all for my absent students at home so they can see what we did. All right, beautiful. Let's go ahead and talk about question number 6. Go ahead and answer.
We said it's an exponential graph because it's always the slope is always increasing. I guess yeah, and then that's it.
What did you guys get the same thing? For your position time graph, did you get an exponential or an upward facing curve? How many did not get that graph? It might have looked slightly linear for some of you, but if you look closely, you should see that those slopes continue to increase. Very good. All right, question number 7. Can you use the y equals mx plus b equation to write a mathematical model for this graph?
We said no because the slope in mx or y equals mx plus b equation does not account for the change in slope because it's always constant. And then in an exponential equation, the slope is always not constant.
It's not constant, it's always changing. So I like that you actually observed it wasn't exponential, as it is. Let's give group number 7 2 claps. This is the first time that we're writing a mathematical model. And our original graph is not linear. So let's go into question number 9. This one is group 3. Let me have group 3 come up and present question number 9. This one is asking, why do you have one fewer average velocity values and midpoint time values than you do position and time? And this was a question a lot of students were like, I have no idea what you're asking. I'm totally confused.
So we say that you have to use 2 value points to find the average value for each segment.
Good. We have 10 different position time graphs, and you need to take pairs of values or pairs of data points to get one velocity data point, right? So for every 2, you get 1. If I have 10, I get 1 less than 10. That's how you end up with 9. Any questions on this problem? This is the one a lot of students struggle with. Let's give group 3 2 claps. All right, moving on. We are doing question number 14 and 15, mathematical model and equation. Oh.
Okay, so we've done this a few times. 5% rule is just y-intercept over the max y value times 100. So we plugged that in, got 32.25%. So we're going to keep the y-intercept in the final equation, which is velocity equals slope, which is for our project at least is 0.251 centimeters per second, times time plus the 1.2 centimeters per second.
Good. So we've got a mathematical model here. Your mathematical model is going to be different. They're not supposed to look the same. But what I do want to make sure of is, did anyone cancel out their initial velocity? Any groups cancel out using the 5% rule? Everyone kept it, yeah? Did we have one group cancel it out? Okay. So we're going to talk about what that initial velocity means. If you canceled it out, that's fine. That's still correct. But some groups had to keep it, and there's a reason why. Tomer. Good question. So this group put units of centimeters per second divided by seconds. That's great. If you reduce it mathematically, you could also get centimeters per second squared. They do mean the same thing. So I use them interchangeably, you can use them interchangeably. And then your y-intercept unit has to be centimeters per second, not centimeters per second squared. Let's give group, any questions on group number 1? All right, 2 claps for group 1. Our mathematical model should look very similar with a different slope and a different y-intercept. Let's go on to number 18. This is group 2, number 18.
Okay, so this would be this. So like the slope is 0.251. Yeah.
Alright, so for 18, the question was, what does the slope of a velocity time graph represent? We put the velocity of an object over a period of time.
It's the velocity over a period of time. One thing that I want to add to this was Chalmers' comment. Actually, can you write this down? Centimeters per second squared. So it is definitely, and you can just good. It's definitely velocity over a period of time. But we've seen a unit very similar to this before, centimeters per second squared. Can anyone tell me where this unit popped up? We also noted it as newtons per kilogram. But let me have Tomer, since this is your group.
Acceleration.
Acceleration. So let me have you write down. Acceleration is the same thing as velocity over a period of time. Go ahead and write that down. Acceleration. This is what I want you to put for number 18. Acceleration is the slope of a velocity over, a velocity versus time graph. Perfect. Good. Are there any questions on how we got acceleration? Centimeters per second is the change in speed over change in time, and that's the unit I want you to use in your mathematical model. Perfect. Any questions on group number 2, question number 18? Let's give group 2 claps, please. Good. Question number 19 is group 6. Let me have group 6 come up. Oh, stop.
No, I didn't. But she said it was good. She said it
All right. And go ahead and start.
Our question was, what does the y-intercept represent? And we said it represents where the object starts. And we know this because the line starts on the line.
The y-intercept is where the object starts. So can we be more specific? Question or comment?
It's the starting velocity.
It's not necessarily the starting position, which a lot of students get mixed up, but it's the starting velocity. So make sure you include, it's not the starting position. Let's do group number,
Yeah, we don't need to.
4. Group
Once we
number
got
4 is doing number 20. You should be making corrections on your worksheet if you did not make them.
Hey, Kiana. So we can give that group 2 claps.
You did, everyone clapped.
I think we get extra points.
Okay, no points. Okay, go ahead and start.
Velocity is equal to acceleration times time.
Velocity equals acceleration times time. So, hold on. I had a lot of groups, and I want to pay attention closely. A lot of groups put position equals. I want to make sure that if you put position, change it to velocity. This is a velocity time graph. Why couldn't we create a mathematical model out of position time. This was one of your questions. Why can't we make a mathematical model out of your position time graph? Why not? What is the
Slope.
There's no slope. Why is there no slope? What does it look like?
It looks like
This.
A curve. We can't make a linear equation with a curved graph. So it has to be velocity equals acceleration times time. How many of my groups actually kept their y-intercept? Did your 5% rule have you keep it? I have 1, 2, 3, 4. 4 groups out of 7 kept their y-intercept. So do you think we should add our initial velocity to this equation? Yes.
So.
So let's add initial velocity. I'm going to call it VI, V initial, because the initial velocity doesn't have to start at 0. Initial velocity, you could have a wheel that starts with a certain speed. I could have pushed it and it started at a certain speed. So let's keep our initial velocity in the equation. So our equation is velocity equals acceleration times time plus initial velocity. And in your mathematical, in your worksheet, it calls it V final instead of just velocity, but it's the final velocity. Make that change on your worksheet, and let's give group number 4 to class. This is a perfect segue into your work for your Wheel Lab CER. So, basically, what you are doing in the Wheel Lab CER, I'm going to give you 2 class periods, so it's not going to be due, Karsten. It's not going to be due till next Monday. I see you Monday, right? So here's what you're going to do. Shh. Let me zoom in real quick. You're going to answer this question. What is the mathematical model for objects that are not moving at constant velocity, meaning the velocity is changing? Anything with a change in velocity is going to give you a curved graph. So we're using the equation from our physics helper. It is under non-constant velocity. So you're going to see it right over here. Non-constant velocity, V final, VF, is equal to acceleration A times time. Ayush. This is your mathematical model. Plus V initial. Okay? This is the mathematical model you guys created, or at least attempted, for your Wheel Lab. Okay, everyone has a couple of data tables. You have a graph. Actually, you have 2 graphs for this lab. And what I want you to do is write a claim evidence reasoning statement that proves every part of your equation. Okay? So you need to prove your variables. Your variables are the final velocity and your time. That's your X and Y axis. You need to prove your slope. Why are we using acceleration for slope? We kind of talked about it in class today. You want to talk about your initial velocity. Some of you dropped it, but others did not. Actually, majority of the class didn't. And the reason why is because when you have your Wheel Lab, your wheel doesn't always have to start off at 0. Okay? So if I set this up and I decided I'm not going to start it at rest, I'm going to give it a little push. That little push is my initial velocity. It also goes for objects that are thrown upward. When you throw an object up, you start with an initial velocity. So what I want you to do is you've got sentence frames. These will help guide you in writing a really well-written CER. You've also got, and these are all handouts, types of error because everyone is going to have a position time graph or a velocity time graph that doesn't fit a perfect line, right? So let's say this is your velocity time graph. Did all your dots fall perfectly in line with your linear equation? Definitely not. I saw some outliers. You need to explain why you have outliers. What happened in your data collection that caused your data not to be perfect? And I do not want to see human error as a reason. That's going to be minus points. The next thing I want to talk about is this rubric, but more than anything, you can see how you're going to be graded. Down here at the bottom, I have examples. So you can see this is what a bad claim looks like. This is what a good claim looks like. In this example, I'm proving the equation for circumference and diameter. I say C equals pi times D. For your claim, you're going to say velocity final equals acceleration times time plus velocity initial. That's your claim. Your evidence is going to be from your data. So I provided a graph for circumference and diameter. This is my data. This is a piece of evidence. What a lot of students do is they tell me their reasoning under their evidence. Evidence needs to be either data you collected, something you observed, or anything that happened within your lab. Do not pull any information from your textbook. Do not pull in any information that you looked up on the internet. It has to be something that you collected or you observed within the lab itself. And then last but not least is your reasoning. Your reasoning takes whatever evidence you provided, whether it's your graph, your slope number value, whatever it is that you gathered, and it brings it back to how that piece of evidence proves your equation. Okay? So, this is your second CER. The first CER was very different because you have lab stations and you described what you observed. This CER is proving an equation. We now have data, we have graphs, and I want to make sure that you prove all the 4 parts of your equation, your variables, your slope, your y-intercept, and why you don't drop your y-intercept. Some of you might have, but as a class, we know we should not, and I want you to explain why. Questions? All right, so you've got 2 class periods, which means you've also got the weekend to work on this. I will be in here during tutorial, so come and see me if you need any help.